For our next big chapter test, we're going to cover all of chapter 6 as well as section 5.6. This is the only section from chapter 5 that we will end up covering. And the reason for covering this, it covers exponent rules and scientific notation. The reason for covering this is when we look at stuff in chapter 6, there might be some situations where a few little exponent rules will really help us out, okay? So scientific notation, it's also helpful. You see scientific notation probably more so in science classes than you do in math classes at this level, but it's a good thing to know and learn, okay? So what I think I'm going to do is the first several topics are really, really short. So I think I'm going to do one video for the first 3 topics. So it'll be one kind of longer video instead of 3 really, really short ones, okay? So for topic 1, we have the product rule for exponents, okay? So when you have exponents, there are different rules that make simplifying exponential expressions just a lot easier, okay? So before we dive into this rule, I do want to just make sure everybody's on the same page. Exponential notation. Exponential. I have no idea why that just all of a sudden switched to red. So exponential notation is the use of exponents in place of repeated multiplication. I've got a little picture of my face in the way. Let me scoot it. Repeated multiplication. So that is quite literally what exponents are. They're just a way, it's kind of like a shorthand way of representing repeated multiplication. So if you have the same thing being multiplied over and over and over, instead of multiplying it over and over and over, you can write it with an exponent. So for example, if I had 2 to the 5th power, that's how we would say that, 2 to the 5th power, okay? That tells me that 2 is being multiplied by itself 5 times. This is not 2 times 5. This is 2 times 2 times 2 times 2 times 2. So 2 times itself 5 times. So this would be 2 times 2 times 2 times 2 times 2. And if we were to evaluate this, we would say this equals, well, 32. And if you don't believe me, go to your calculator and prove to yourself it is 32. And just note, 2 to the 5th is not 2 times 5, okay? It is not 2 times the exponent. It is 2 times itself as many times as the exponent says. So when we have these expressions that are in exponential notation, sometimes we have to do some simplifying, and it can be really, really helpful if we learn these different rules. It's just kind of like shortcuts to working with exponents, okay? And the first one we're going to look at is called the product rule for exponents, okay? So if you are multiplying 2 or more exponential expressions with the same base, I'll explain base in just a minute, keep the base and add the exponents. When we're talking about the base, okay, this is the thing being multiplied repeatedly, okay? So this is I'm going to go ahead and say thing. It's not real fancy, but the thing, okay? So it's the thing being multiplied repeatedly, okay? So if you have a base that matches, even if the exponents are different, if you have 2 expressions that have the same base, we can easily combine them. And the way we do that is we keep the base and we add the exponents, okay? The exponent being that little number in the corner, which tells us how many times to multiply our base. So let's just kind of do a for example here. If I had x to the 3rd times x to the 2nd power, okay? This means I have x multiplied by itself 3 times, and then I have x again multiplied by itself 2 times. So I have 2 expressions that have the same base. This would be exactly the same thing if I wrote it out longhand as x times x times x, that's my x to the 3rd, times x, which is x to the 2nd. So if I look and count how many x's I have 5 of them. So this is really x to the 5th. Now that is the long way to do this. The product rule says, hey, there's a shortcut to this. I know you all can see this bug. Don't think I'm like nasty and have bugs. It is so beautiful out tonight that I've got the door open. And so I have a dinner light on and the bugs just flock to me. So it is what it is. Anyway, these exponent rules give us a shortcut for dealing with exponents. The long way to solve this problem would be to write out the 3x's, write out the 2x's, and then count how many x's I have. The shortcut is we have two expressions with the same base, keep the base, and add the exponents. Let me rewrite that. That looks crazy. Equals x to the 3 plus 2, or x to the fifth. So notice, no matter how we solve this, we get the same answer, okay? Now, something like this with exponents of 2 and 3, it's not a big deal. We could do it longhand. We could do this rule. But what if we had exponents of 50 and 62? We wouldn't want to write out 50 x's and then 62 x's and then have to go through and count them. Instead, we would just add those exponents and keep the base, okay? So let's go ahead and practice this one. Example 1 says use the product rule to find each product. So for part A, you can see we have 2 to the third times 2 to the fourth. First, make sure your bases match. In this case, they do. So we would say, okay, this has to equal 2. And then because we're multiplying two things that have the same base, we want to add their exponents. So this is like 2 times 2 times 2. And then 2 times 2 times 2 times 2. That's going to give us the same answer. But we're going to use the shortcut. So this is really 2 to the 3 plus 4 power, which tells me this is 2 to the 7th, okay? Now, if you have a base that is a number, go ahead and evaluate this all the way out. If you have variables, just leave the variable with whatever the simplified exponent is. But in a situation like this, I can go ahead and work it out. So if you have a calculator or a cell phone, go ahead and get it out, pull up the calculator app. And we want to go 2 with an exponent of 7, and we get 128. So this equals 128. So if we multiplied out 2 times itself 7 times, we'd get 128. Okay? Now for part B, we have x to the fifth times x to the 7th. So make sure you have the same base. We definitely have the same base, so we're multiplying two expressions with the same base. We want to keep the base, add the exponents. This is x to the 12th power. Okay? And then finally, we have z to the third times z to the sixth, okay? I do want to point out the z in the middle, okay? We are definitely multiplying three expressions that have the same base, but some students get a little bit confused with that z in the middle. If you ever see a variable all by itself, it is technically that variable to the first power. We just don't write the exponent of 1. We're saying, hey, we have this 1x, okay? So just know that if you see a variable by itself, there's technically an exponent of 1. So since we are multiplying all three expressions and they all have the same base, we can keep the common base, which is z, and then we want to add our exponents, which would be 3 plus 1 plus 6, which is z to the 10th. All right, so that is the product rule for exponents. So in your mind, think product. I'm multiplying two things that have the same base. Okay, now for topic 2, again, I'm going to do topics 1, 2, and 3 in the same video. For topic 2, we have something that is similar but completely different, okay, which I know is frustrating for me to say, but these two rules, the product rule and then what we're getting ready to talk about, the power rule, they're sometimes easy to confuse, so make sure you really understand the difference between the two. So the power rule for exponents is a situation where you have an expression that's in exponential notation all by itself, but you have raised it to a second power. So you have like double exponents on a single base, okay? So when an exponential expression is raised to a power, so that means you already have something with exponents raised to an additional power, we keep the initial base and we multiply the exponents, okay? And so let me give you another just really quick for instance. Let's say we had 2 to the 4th squared, okay? Well, this would be the same thing as saying we have 2 to the 4th times 2 to the 4th. The initial base here is 2, but the actual base is really 2 to the 4th. So that means that entire 2 to the 4th has to get multiplied by itself 2 times. So we have now, by rewriting it, we have a product rule. So this is really 2 times 2 times 2 times 2 times 2 times itself 4 more times, or 4 times. So we end up getting 2 to the 8th power, okay? Well, instead of doing this the long drawn out way, what we can do, let me write it down here so it's a little clearer because I'm going to show you the shortcut. So what we can do instead is use this shortcut. This shortcut says, hey, if you have something with an exponent raised to a second exponent, keep the initial base and then just multiply your exponents. So we would say, hey, this is really 2 to the 4 times 2 power, and it just so happens 4 times 2 is 8. So you can do it the long way, you can do it the short way. With something like exponents like 4 and 2, it's not that big a deal to do it the long way, but really embrace the shortcut, because what if these exponents were 40 and 29? You'd have a gazillion little 2's multiplied out by each other. So there is some power behind these rules, okay? So let's go ahead and look at example 2. Example 2 says use the power rule to simplify each expression. So for part A, we have 2 to the third raised to the second power, so very similar to what I just showed you. So using our shortcut, we can say to ourselves, hey, do we have something with an exponent raised to a second exponent? We for sure do. Take the initial base, which is the 2, and then you want to raise it to the product of your 2 powers. So we're going to raise it to those powers multiplied together. So this would be 2 to the 6th power. And again, just like in example 1, if you have a situation where your base is a number, go ahead and multiply it all the way out. Go ahead and evaluate that expression. So if you've got your calculator out, you want to take 2, raise it to the 6th power, and we get 64. And it did just occur to me that maybe you don't know how to do exponents on your calculator. The only calculator that I have, like electronic, like virtual, I don't know what we want to call it, but the only calculator I have access to is a graphing calculator, but I can show you very quickly how to do exponents on that. If you have another calculator, we may have to talk in person or on Zoom to determine how to do exponents. But for now, let's go to my calculator so I can show you. I think it's this screen. It is. So here's my calculator. It looks a little funny compared to an actual graphing calculator. This big screen on the right kind of represents the screen on top of a graphing calculator, but this is so much better than it used to be. So we love the new improved virtual TI. So what you want to do is type in your base, okay? In this case, since our base is just positive 2, I can just leave it as is. I don't have to put it in parentheses or anything. So I want to hit the 2. And then if you look to the far right, starting at the bottom on the far right, you have your enter button. That's kind of like equals, plus, minus, multiplication, division. And then above division, you have this like up arrow. It kind of looks like a roof on a house. That is called the caret button, and that will raise you up to that superscript exponent world. And then type in your exponent, which I believe was 6, and hit enter, and we get 64 that way. So that's how you can type in exponents. There are other shortcuts, like if you're just doing an exponent of 2, there's a simple way to do that, but this kind of will let you type in just any exponent. Okay? Let's go back to example 2. So let's look at example 2, part B. So we have an expression x to the 5th that is raised to another exponent. So we're going to take the initial base of x, and we are going to raise it to the 5 times 7 power. So we end up getting, well, 5 times 7 is 35. So we get x to the 35th power. And then finally, we have z to the 3rd. So that's kind of the big base. And then that has been raised to another power of 6. So we're going to take the initial base, the base of that inside expression, which is z, and we are going to raise it to the product of those 2 powers. So 3 times 6, and that gives us z to the 18th. Now, I am not going to sit here and test you on your multiplication tables, okay? So if you don't know right off the top of your head what 3 times 6 is, you're still a wonderful, lovely, amazing person. But there is some power to kind of practicing those multiplication tables and bringing it back to the surface, okay? Let's go ahead and move on to topic 3, and that'll wrap up this video. So for topic 3, we have I can't talk. We have the quotient rule for exponents. So in math, the word quotient means divide. So this one is very, very similar to the product rule in that in the product rule, we were multiplying 2 expressions that had the same base. Here, for the quotient rule, we're going to divide 2 expressions that have the same base, okay? So when dividing exponential expressions with the same non-zero base, that is really important. As long as you have a non-zero base, you keep the base, but this time you subtract the exponents. So let's just kind of look at a generic example. Let's say we have, I don't know, a to the 4th divided by let me not do 4th. Let me do a to the 5th divided by a to the 2nd. This would be the same thing. A to the fifth is like A times itself 5 times. This would be like A times A times A times A times A. And then A to the second would be like A times itself twice. All right. And the way things work in math is if you have factors, that's things that are being multiplied. If you have factors that are the same in the numerator and the denominator of a fraction, you can cancel them because if you take a number and divide it by itself, you really just get one. So if we look at these A's right here, we can say, hey, a lot of times we get lazy and say they cancel. These divide out to become one. These A's divide out to become 1. So what I'm left with is A times 1 times 1 times A, or just A to the third power. So that's technically what's happening. But let's go ahead and look at the shortcut. The shortcut says, hey, if you're dividing two expressions that have the exact same base, keep the base. So in this case, our base is A. So we can keep the base and then raise this to the difference of the exponents. Now, you do have to make sure you do the top exponent minus the bottom exponent. So order does matter here. So we want to take 5 minus 2, which gives me A to the third power. So you can see whether we do this the long way or the short way, we get A to the third power. Okay, so I'm only showing you the long way so you can kind of get a conceptual idea of what is happening. Okay, so let's go ahead and look at our examples. For example, oh, that should say example 3. Oh, I was copying and pasting and I forgot to fix that. I'm really, really sorry. That should say example 3 so you can fix it on your notes. Example 3 says use the quotient rule to find each quotient, okay? So for part A, we have 2 to the 7th power divided by 2 to the 4th power. So we are definitely dividing two expressions that have the same base, okay? So we can keep the base, and then we want to raise this to the difference. Difference means subtract. We can raise this to the difference of the exponents. Top exponent minus bottom exponent, order does matter. So we get 7 minus 4, which is 2 to the third. And 2 to the third happens to be 8. If you don't believe me, check it on your calculator. Okay, so that is the quotient rule. Now, earlier we did have here that this works as long as your base is non-zero. It is worth mentioning if your base is 0, that means your denominator is 0. And one thing you must remember in fractions, denominators cannot equal 0. Okay, if we had, in this case, if we had 0 to the 7th power divided by 0 to the 4th power, well, 0 to the 4th power is 0. So you would end up having division by 0, which mathematically can't happen. We say it's undefined. Okay, so that's kind of what they mean by you can't have you have to have non-zero bases, which means your base can't be 0 because then your denominator would be 0. Okay, now moving on to part B, we have x to the 10th divided by x to the 6th. We are certainly dividing two expressions that have the same base. We're going to keep the base of x, and we are going to raise it to the difference of the exponents, top minus bottom. So 10 minus 6 is 4, so we get x to the 4th power. All right. And then finally, for this video, we're going to wrap it up. We have z to the 8th power divided by just plain old z. And remember, if you have just a plain old variable, it's technically that variable to the 1st power. So we don't generally write the 1, but just know it's secretly there, okay? So we would say, hey, we're dividing two things that have the same base. We want to keep the base of z and then subtract the exponents, top minus bottom. So we get 8 minus 1. This would be z to the 7th power. So those are kind of the three main exponent rules. There are more of them. We have something called a product to a power rule. We have a quotient to a power rule. We do other kind of complicated simplifying, but it doesn't really happen in this class. It would be more like an intense algebra class. So these are the main three, and then we're going to look at two other things that can happen with exponents. We'll do that in our next video. Okay, so that's going to be it for the first video. In the next video, we'll talk about the zero exponent and negative exponents.